We're going to carry out a ZE test. Now obviously to carry out this test I need to take the cover off of the distribution board. Before I do that I must isolate the system. So I've isolated it and locked it off. Everything's safe now. But it's still a live test, so great care must be taken at all times. I've disconnected the earthing conductor because I don't want any parallel paths. So when I do the test, I just need to know the resistance between here and our supply transformer. To carry out the test, I need an earth fault loop impedance test instrument, okay? With leads to GS38, the contacts need to be covered as maximum as possible, okay? To do the test is a simple process. I can put this instrument on a high current. I need to connect the crocodile clip to the disconnected earthing conductor and then just test between one line, incoming line to earth, and I've got a value there of 0.17. But of course I need to know the highest value, so I need to do the test between all three lines. 0.17 and again 0.17. So they're all consistent. So my value of ZE would be 0.17 of an ohm. We're going to carry out a test now to confirm the integrity of a protective bonding conductor. Obviously this is a dead test and we're going to have to disconnect the bonding to carry out the test properly. So first thing I need to do is isolate the installation, lock it off and make sure I've put the proper labels and locks on so that it's entirely safe. I then need to disconnect the bonding conductor, which I'm going to test. Because this bonding conductor could be quite a long conductor, it's going to be what we call a long lead test. To carry out a long lead test, obviously I need a long lead, or I can use a long piece of cable, but it is much better to use the right type of equipment if you possibly can. The problem with this long lead, of course, is that it's going to have a resistance of its own. So for this test, I need to zero the leads, taking into account the resistance of this lead, okay? So what I do is I join the two ends together, the crocodile clips together, having plugged one end of the lead into the test meter. The important thing when you're zeroing leads is to ensure that you get the crocodile clips connected around the right way. If we look at a crocodile clip, we can see that this is a solid connection through there, whereas the jewels on this side are on a spring. We need to make sure that when we connect them together, we get the two solid connections touching each other. It might sound silly, but actually, we're measuring very low resistances here. Once I've done that, set the tester to ohms, let the machine settle, then I push the button and we can see that I've now zeroed the leads. So any resistance value that I measure now will subtract the value of this lead. Of course, another way we could do it is to measure the resistance of the lead, write it down, take a reading, and then subtract the resistance from this lead at the end of the job. Okay, so we need now to measure from end to end. The value which we must be below, as far as guidance note 3 tells us, is 0.05 ohms. Can create a slight problem because guidance note 3 also tells us that these instruments have to be accurate between 0.2 and 2 ohms. So we're measuring something that's very, very low. Some of these instruments really aren't that accurate. This one's okay, but not all of them are. So a good measurement, really, a good way of measuring it is in length. For a 10mm bonding conductor, up to about 25 meters would be okay. If you get above 25 meters, you should really be looking at a 16mm bonding conductor. But we'll carry out the test anyway. First thing I need to do then, of course, is connect the end of my green lead to the disconnected bonding conductor. And this is bonding the gas. And then I need to go off and find the gas meter and do another test at the gas meter. So now we're at the gas meter. Just going to carry out the final part of the check, and of course that's to measure the resistance of the main or the protective bonding conductor. Whenever I do this test, I prefer to use a connection on the pipe work rather than the clamp, because what that's doing me now is telling me that the integrity of the clamp is very good. There's a good joint between the clamp and the pipe. If there was dirt or corrosion underneath it, the resistance would probably be quite high. So you can see now I've got a reading of 0.02 ohms, perfectly acceptable for this installation. As I said, the value that we should be thinking of is 0.05, so this is quite low. One other good thing, which is a bit of a tip, sometimes as electricians we're not sure which side to connect the bonding conductor. If you look on the top of a gas meter, there's generally a chevron or an arrow. It's not really there to help electricians, but it can be. If you connect your bonding conductor on the side that the arrow is pointing to, you're never going to be wrong. So, and also of course, we need to make sure that the clamp is before the first joint. There's often a bit of confusion as to whether or not protective supplementary bonding is required in a bathroom. Modern installations, of course, are very often plastic pipes, and all bathrooms now have to have protection with a 30 milliamp RCD. The requirement for whether or not it requires bonding is we need to take a measurement between a known earth and whatever it is we're not sure wants bonding or not. The regulations give us an example or a formula that we should use. Where we're using an RCD, instead of using the current which is going to cause the automatic disconnection of a circuit protective device, we use the current which is going to cause the operation of an RCD. Consequently, the formula is 50 volts divided by I delta N. Okay, so I delta N in this case for a 30 milliamp RCD is 0.03. If we divide that into 50, it gives us a value of 1,667 ohms. So the measurement we need to take really is between a known earth within the room, if possible, to whatever piece of metal we think may or may not need bonding. If the resistance between the two pieces of, or the earth and the piece of metal is less than 1,667 ohms, it doesn't need bonding. It's considered that that resistance is low enough. If it's above 1,667 ohms, then it does require bonding. The problem we've got when carrying out this type of measurement is that very often our instruments won't measure 1,667 ohms. A lot of them only go up to 99.9. If you're lucky enough to have one that measures kilo ohms, then that's fine. But if not, we have to take another approach. Guidance notes tell us that the maximum shock current that we should really permit in a bathroom, none at all really, but you know, in the event of a fault, would be 10 milliamps. And from that, we can work out our resistances between pieces of equipment to see whether or not they're an extraneous conductive part or whether they're just a piece of metal. So if I divide 230 by 10 milliamps, I'm going to end up with a value of 23,000 ohms. That's pretty difficult to measure with a normal piece of equipment. So at that point, we would have to go to an insulation resistance tester. Now, what the regulations also tell us is that from fingertip to fingertip, we have a resistance of 1,000 ohms. So we can subtract the 1,000 ohms from our 23,000 ohms, which would leave us the maximum resistance permitted between a known earth and the piece of metal which we're trying to test. That's a difficult value to measure with a normal low resistance ohm meter, so we're going to use an insulation resistance tester. Of course, the insulation resistance tester won't measure very, very accurately, but it will give us an indication. So if we measure between our known earth and the piece of metal which we're not sure wants bonding or not. If we get a value of 0.02 megohms, which is 20,000 ohms or less, then it is an extraneous conductive part and it should be bonded. If we get a value of above 0.02 megohms, then it's just a piece of metal. And I'm going to carry out an R1 and R2 test on a radial socket outlet circuit. I've prepared the board ready, I've isolated everything and carried out all the safe isolation procedures as required. Again, I'd like to stress that when you're working on around or on live equipment, as we are now, we need to be very, very careful because, one mistake can be fatal. What I'm going to do in this case is I'm actually going to do the test at the board and short out the circuit at the other end, because for a socket outlet circuit, I sometimes find that easier. What I'm going to use is a plug, a test plug, and I'm going to put a lead in it like so. I know the circuit's isolated, so there's no problem. I've tested it. I'm going to plug this in, then I'm going to come back here, carry out the test. I've isolated this circuit. This is the furthest point on the circuit, which is the one I want to take the R1 and R2 reading from. What I need to do now is obviously zero the instrument to take into account the resistance of the instrument leads and also the piece of equipment I'm using for carrying out the test. So quite a simple process. I'll just turn my instrument to ohms, take a reading, push the button, and when that little symbol comes up on the bottom left-hand corner, that's showing me that this is now zeroed. I can plug this in, go back to the board, test between line and earth, and that will actually give me the R1 and R2 reading that I'm after. I've inserted the plug and shorted out the other end of the circuit. I've zeroed the instrument, as you saw earlier, and now all that remains to be done is to carry out the test. But as I said earlier, you must be very careful because there are live conductors around. I've now got a value of 0.2 of an ohm, which is perfectly satisfactory for this circuit, although I'll check it later. I just need to record it on the schedule of test results. Make sure I remove my lead from around by the end of the circuit and replace everything safely. Very often you can encounter problems when you're trying to measure R1 and R2 on a three-phase circuit which has a motor starter or a contactor in it. If it's a contactor, it's not too much of a problem because you can just push the contacts together and you'll get a reasonable reading. Where you've got a motor starter which has got overloads in it, thermal overloads particularly, the thermal overloads have got a high resistance wire, so when you take a reading you get a very high R1 and R2 reading, which of course isn't an accurate reading at all. I'm going to show you how I get over the problem. There's obviously other ways. First of all, we need to make sure that the board is absolutely isolated, okay, locked off as it should be. We need to use a low resistance ohm meter. Obviously we need to zero the leads. So if we do that before we start, turn the instrument on. When we connect the leads together, we need to make sure that we've got the solid part of the crocodile lead touching the solid part of the other crocodile clip so that we don't end up with high resistance joints. Once I've got a reading, if I push the button, zero the instrument, that's that part of the job carried out. So what I've got is I'm going to test to a three-phase plug and we've got a starter in the circuit. What I've done is I've wired up a three-phase plug and obviously it's got three phases, but I've joined them together so that I only need to carry out or just join the crocodile leads once rather than mess around trying to swap between different wires. It works perfectly well because the only bit of resistance I've got is this piece of cable. So if I plug this into the socket first and then connect my crocodile clips. Need to make sure they're pressed together nice and tight so that I don't get a high resistance joint. Now I've done that, I need to connect each phase or each line into the earthing bar. The easiest way to do that is disconnect each one individually, connect it into the earth terminal. I could, if I want, do them all together, which is probably for the sake of this, the easiest way to do it. So that's what I'll do now. As you can see, I've connected all three of them into the earth terminal. It may seem a bit strange, but actually I'm still only going to be measuring L1, L2 and L3 individually because I'm going to bypass the starter. As with all motor starters, we've got an overload device, which obviously prevents the motor from overloading. If we try and measure across that, we're going to get a high reading, as I said before. So the easiest way to do it really is just to get a short lead and just short out between the incoming side of the starter and the outgoing side of the starter, and we'll get a reading. And we just need to do that on each line. So we've done L1, now L2, now L3. And the highest of those we would record as R1 and R2. We're going to carry out a ring final circuit test. And for that test we need a low resistance ohm meter with the leads zeroed. We need to turn the instrument on to ohms, join the leads together. If I push the button and then zero the leads. As you can see, I've already disconnected the leads from the distribution board. These are our ring circuit leads or cables, and they're identified. It's very important that each end of the ring is identified so that we know which one goes to the first socket and which ones come from the last socket. These are just identified with a bit of grey tape. Most people can use tape or numbers or whichever way you prefer. As long as they're identified, it doesn't matter. I now need to measure the resistance end to end of each conductor. Because these are the same size conductors, they're all going, or should be, the same value of resistance. So I'll measure this, 0.23. Now I do the blues or the neutrals. It should be within 0.05 of 0.23, so that's close enough. And again, I now need to do the browns or the line conductors end to end. And the value should be very close to 0.23. What I need to do now that I've got the measurement of 0.23 for each conductor is join together one marked line conductor to an unmarked earth conductor and a marked earth conductor to the unmarked line conductor. Might sound complicated, but basically I'm going to join the marked one to the unmarked one on both occasions. As you can see, I've now joined one marked one to an unmarked one on each case, so you've got a cross connection, which is really a figure of 8. Make sure the connections are tight, so it's usually better to use a block connector if you possibly can. What I'm going to do now is take a measurement here to give me an indication of the value which I should get at each socket outlet. In reality, it should be half of one of the original measurements, so 0.11, 0.12 would be what I'm expecting to get. Okay, that tells me what I should get now at each socket between line and earth. I'm going to carry out a test between line and earth at each socket. Need to make sure the switch is turned on, of course, and I'm going to use a little test box. I'll plug that in, place my 2 probes between line and earth, and I should get a value of between 0.12 and 0.17. Providing it's within 0.05 of the original measurement, I haven't got a problem. And that should be the same for each socket outlet. I'm now at the last socket, I'm just carrying out the final test. Up till now, they've all been within 0.05 of the original value. take the reading again and again, perfect reading. That tells me that all of these sockets are on the ring. The highest of these these values which I've taken, I'd record down as my R1 and R2 value for the ring. But of course, my job's not finished yet because I still need to use line to neutral connections to make sure that the polarity of the ring is correct. I've now cross-connected the line and neutral conductors. It doesn't really matter whether you do the line and neutral first or the line and earth first. There's no preference, but of course the value you record is the one between the line and earth. I need to go again round every socket and test now between line and neutral. Need to make sure the switch is turned on. Put my probes in, and I should get a value again of around 0.15. I'm now at the last socket, just going to repeat the test again. Up till now, all of the values have been correct. If I take a reading, again, the value should be around 0.15. And as I said, providing it's within 0.05 of the original value, we haven't got too much. Part of the inspection and testing process for an initial verification is an insulation resistance test. So here, we're going to carry out an insulation resistance test on the complete installation before the tails are connected. What we need to do is make sure that all of the circuit breakers are turned on, the main switch is turned on. Again, we need to remove all of the lamps, bypass any dimmer switches, remove anything from the system which is likely to be damaged by the high voltage because we're going to test at 500 volts, or even neons which may not be damaged but of course will give us false readings, and then again we'll be looking for a fault that may not be there. So we need to just take care that we prepare the installation ready for test before we test. Okay, so I've done that. Next thing, I use an insulation resistance tester. This is a multi-function instrument, but all I need to do is turn it on to 500 volts because this is a 500 volt DC test. I've got to make sure that the tester is working properly. So I need to join the leads together, push the test button, and I should get a reading of 0. Take the leads apart, push the test button, and it should be over range, and this meter goes to 999 megohms. Once I'm sure the instrument's working properly, just one final check is to make sure that the leads are to GS38. Obviously, it's a 500 volt test, and anything over 50 volts, the leads do need to comply. First part of the test really is test between live conductors, just using crocodile clips, making sure that they're nice and tight. Push the button, and I've got a value which is 999, which is perfect. Any value over 2 megohms would be acceptable, but of course 2 megohms really seems quite low, and on a new installation we would really be looking for 999, or at least, depending on the instrument you've got, it should be over range, higher than we can measure. Once I've done between live conductors, I'll do a line conductor to earth. Again, push the button, keep it pressed, and I should get a very high reading again. Next part of the test, neutral to earth, push the button, and again a very high reading. And we must also remember that while I'm carrying out these tests, I should go around switching any two-way switches on and off just to make sure that I'm measuring the whole circuit. Of course, rather than measure between line conductor and neutral conductor separately, I could, if I wanted to, join the two together and carry out a test like so. And if the test again is of a very high reading, there'd be little point in testing between neutral and earth and then line. I'm going to do an insulation resistance test on a 3-phase board or 3-phase installation. Rules apply always, of course, that we've got to make sure it's safely isolated because it's a dead test and we need to use the right type of equipment. Before we start, we need to make sure that anything that could be damaged by the test voltage is disconnected, isolated or bypassed. Any dimmer switches are bypassed, lamps removed if possible. Just those sort of precautions for two reasons. One, we don't want to damage the equipment, and two, it will give us false readings anyway, and we'll be looking for a fault that may not be there. So first part of the test, or the first part of the job, is to check that everything is disconnected as should be. As far as the board goes, the board is isolated, but we need to make sure that all of the circuit breakers are on, because we're going to test the complete installation. We're going to use an insulation resistance tester, and we're going to use a test voltage of 500 volts. Because it's a 500 volt test, you have to push the button to liven up the probes. And for that reason, of course, you do need to push the button. So you're going to, if you're not careful, it can be very difficult trying to hold probes on and push the button at the same time. I've got a special probe here which has got a button on the end of it which allows me to operate the device from the probe, which is obviously a good idea, makes life a lot easier. One of the first things I need to do when I'm carrying out an insulation resistance test is to make sure, of course, the probes are in good condition, the ends of the probes are protected to comply with GS38, because this is really a 500 volt test. GS38 applies to any equipment over 50 volts. I also need to make sure that the instrument is working properly. So to do that, first of all, I need to do a test with the leads together, push the button, and you can see I've got a very low reading. In fact, I'm getting 0. Carry out the same test with the leads apart, push the button again, and now the reading should be over range. Okay, with that done, I know full well that the instrument is working properly. So all I need to do now is go to the board and test between, first of all, line and neutral, push the button, and again I've got a reading that's over range. L2 to neutral, again reading over range. L3 to neutral, again reading over range. L1 to L2, reading over range. L1 to L3, reading over range. L2 to L3, reading over range. And of course, while I was carrying out those tests, particularly the test between live conductors or line conductors and neutral, I should go around and operate any switches which may be controlling lights and devices, just to make sure that I'm testing the whole of the circuit. The other test I need to do, of course, is between all live conductors and earth. So make sure the probe's secure onto an earth point, test between neutral and earth, should be over range. L1 to earth, again over range. L2 to earth, again over range. L3 to earth, again over range. Just to make sure the machine's still working, probes together, and I've got a reading of 0 again. And that's an insulation resistance test on a 3-phase installation. We're going to do an R1 and R2 test on a lighting circuit, and at the same time prove that we've got polarity. In other words, that the switch is in the line conductor, which obviously is part of our inspection. You can see I've got the board locked off. It's nice and safe. I can work on it. There's notices. What I need to do to get an R1 and R2 test is to join the line conductor of the circuit I'm testing with the earthing conductor. So the easiest way really is just to disconnect it and put it into the earth bar of the board. There are other ways, of course, but in this instance, this is probably the easiest. Okay, I need to get a nice tight connection on this because I don't want a high resistance joint, which will result in us having a very false reading. Okay, so I now need to go to the light that I'm going to, or the light point that I'm going to work on. If I just take it apart for a second, I don't need to disconnect anything. I now need to make sure that my meter is going to be reading accurately, so I need to zero the leads. First of all, I set it to ohms, hold the ends together nice and firmly, wait until I get a reading, push the zero button, and the leads are now zeroed. So when I take a resistance value, I'm actually just going to get the resistance of the cables rather than the resistance of these leads as well. So now we've exposed all of the conductors that we need to be working on. I just need to connect my leads. So first of all, one lead goes onto the earthing point of the circuit, and turn the instrument on. We've already zeroed the leads. I now need to place the probe onto the switch return of the lighting circuit. And we can see that I've got an open circuit here. Okay, that's higher than the value can read. What that's really telling me is one of two things. Either I've got the wrong conductors here, or the switch is turned off, which is giving me a high reading. The way to check it is I now need to go to the switch, turn the switch on, and then repeat the operation. If I place my probe on the switch return again, I should get a much lower reading, and the value I'm getting there, as you can see, is 1.27, and that would be the value that I'd write down for my R1 and R2 of the circuit, providing, of course, this test was carried out on the furthest point. We're going to carry out an earth electrode test now. It's only a mock-up, so I'm using a bit of copper pipe for our earth electrode, but the test really consists of an electrode under test, a potential electrode, and a current electrode down the bottom further away. What I need to do is drive the electrode that's under test into the ground, and I need to measure how far it goes in. The one that I've put into the ground is actually 2 meters deep. The current electrode, which is the furthest one away, needs to be at least 10 times the depth of that electrode away, and the potential electrode needs to be placed in between the two. I then need to connect the ends of the leads into an earth electrode test instrument and take a recording of the resistance value. This is a 3-lead test, so I just need to give the machine a second or two to settle, push the test button, and you'll see that it's reading the potential electrode and the current electrode. And we've got a resistance value there of 80.8 ohms. I've now moved the potential electrode closer to the electrode under test. It needs to be 10% of the total distance between the electrode under test and the current electrode. So as that was 2 meters deep, I've now, and the distance apart was 20 meters, I've moved the electrode 2 meters nearer to the electrode under test. Now I'm going to take another reading. (80.06). The first one was 80.08. Now I need to move the potential electrode 2 meters nearer from the center to the current electrode. I've now moved the potential electrode 2 meters from center nearer to the current electrode, and I need to take a third test. I've got a value of 80.7. What I need to do now is add all 3 values together, divide them by 3 to find the average, and that would be the value I wrote down. If I'm working on an installation that requires a much lower resistance value, earth resistance value, all I need to do is insert another earth rod. And the rules are that I would need to insert the earth rod the distance away from the original earth rod whichever the depth of the original earth rod was. So we knew that this one's a 2 metre deep rod. I need to move 2 metres away and insert another one. I've already carried out that process. Just want to take a resistance value to see what difference it makes. We can see now that we've got a resistance value of 51.5. It's dramatically reduced the resistance value, so 2 earth electrodes would be better than 1 in this instance. And to get a very accurate reading, of course, what I would need to do now is repeat the 3 tests by moving the potential electrode 10% this way, 10% the other way, and taking an average of the 3 readings. And that would give me the reading I would write down on my test certificate. What we're going to do now is we're going to do a ZE test on a TT system. As you can see, I've already isolated the consumer unit, locked it off, put the labels up so it's quite safe. I've disconnected the earthing conductor because when we take this test, this measurement, we don't want any parallel paths included in the result. I have to use an earth fault loop impedance tester. And what I'm going to do is I'm going to connect one of the crocodile clips to the disconnected earthing conductor, turn my earth loop impedance tester to high current because there are no RCDs in this circuit, and then I'm going to take a test between the incoming line, and you can see there we've got a reading which is 2.18 ohms. That's quite low for an earth electrode. The reason for that is that very, very wet outside. It's been pouring with rain for ages, and consequently we're getting a very good reading. Once I've completed the test, obviously I'll remove the leads, make absolutely certain that I'll reconnect the earthing conductor, and then at that point I can take off the padlock and reinstate. What we're going to do is carry out a ZS test on a lighting circuit. There's several ways of doing it, but the ideal way and the easiest way, particularly if there's an RCD in the circuit, is to use a test instrument which will allow you to take the test using 2 leads and a very low current so that it doesn't trip the RCD. You have 2 options using this type of instrument. One, you can do it at the switch between the switch line and the earth, or you can do it at the lighting point between the switch line and the earth as well. Whichever's your choice. Very often the lamps are quite difficult to reach, so sometimes it's beneficial to do it from the switch. And of course, if you're using 2 leads, you don't need the neutral, so that's the benefit of this machine. First of all, I need to look at the protective device, which is protecting the circuit. And for this one, I can see that it's a type B 6 amp BSEN 60898. What I need to do now is look on the chart, which I've got in guidance note 3 or the on-site guide, and that will give me the value, the maximum value of ZS that the circuit would be allowed to have or permitted to have. The value for this particular device is 6.18 ohms. So now all I need to do, make sure everything's switched on, is go to the light point and take a value between the switched return and the earth with the switch turned on. Need to set my instrument to LPE and Z because that's what I'm doing. And because I'm using 2 leads, you can see the instrument tells me that it's a low current test. This won't trip the RCD. That's the whole object of the exercise. If I did it on a high current test, it will allow too much current to flow through the RCD and it will trip it. So low current test is very important where RCDs are involved. Okay, what I need to do now is place my probes, one on the earth and one on the switch return, and push the test button. Because it's pulsing at a very low current, it's going to take a little bit of time, not too long. It always seems a long time when you're waiting, but literally just a few seconds. And I've got a value of 1.08 ohms. That value is perfectly acceptable because it's far lower than the 6.18, which is my maximum. And that's a ZS test on a lighting circuit. Obviously, you need to do it at the furthest point. If you're not sure which is the furthest point, it may be that you need to do it at several points on the circuit, and the highest value that you measure is going to be recorded as your ZS. It's a requirement of our wiring regulations that any equipment must be able to withstand the maximum current that could flow where it's installed. So for that, we need to find the prospective fault current, which is obviously known as a PFC, sometimes known as IPF. That's the maximum current that can flow. Because we need to measure the highest value that's likely to flow, we need to make sure that everything is connected and turned on, because that way at least we'll get current flowing through all of the parallel paths. That's quite important. For that, I need to use a prospective fault current tester. Our earth loop instruments normally do the same job. So for that, I'll turn it on to high current, and then I test between, first of all, I need to know prospective earth fault current, which is the maximum current that could flow between any line, conductor and earth. So with 2 leads, remember this is a live test, so you must take great care at all times. I go from my earthing terminal to our L1. Earthing terminal to L1. And with this machine, I need to push a button to give me PFC. And we can see that the maximum current between earth and L1, or this is an old board, so the red phase would be 2,323 amps. I then can do the test between the yellow phase, or which would be now be known as L2. Up here, look, we can see it's indicated it's the yellow phase to earth. Take a reading, push the button, and I've got 2,071 amps, which again is very close, so that's good. Next, I go to the blue and earth, take another reading, push the button, 2,426. So roughly speaking, 2,400 amps is the highest it can flow between any line, conductor and earth. Next, I need to measure between line and neutral. Again, all lines are neutrals, so I'll go on L1 first, or the red phase in this case. Take a reading, push the button, 2,593. Now between the yellow and the neutral, push the button, 2,290. And now between the blue and the neutral, push the button, 2,297. Now, because this is a 3-phase supply, obviously current that could flow between 2 phases would be much higher. And as a rough guide, which is probably as accurate a calculation as you could get, you would need to double the highest value which we had between line, conductors and neutral. So if we say this is 2,300, if we double it, 4,600 would be the value that we would put down for prospective fault current. Some instruments can test between 2 lines. You need to make sure that your instrument is capable of doing that, because the current that could flow is quite high. This instrument can manage that okay, so just out of interest, we'll do a reading and we'll see what value we get. First of all, I'll go between L1 and L2, or in this case, red and yellow. And I've got 3,488 between red and blue. $4,148, yellow and blue, 3,732. So the highest value there I could put down as quite an accurate reading for PFC. although as you saw the value of line to neutral doubled was slightly higher, which is always going to be on the right side. So whichever way you do it is perfectly acceptable as far as the regulations are concerned, because the value between line and neutral is always going to err on the side. This is a test rig that we use to simulate a TT system. As we know, with a TT system, you would have to have an RCD as a main switch and RCDs throughout the board. Now, sometimes you can use RCBOs for every circuit if you want to, or maybe you want just a split board because of cost, so you've got half of the board with another RCD and 2 circuit breakers. The choice is really yours. You can do it whichever way you like. If you come across a board like this, of course, if we're installing one like this anyway, we need to make sure that if there's a fault on this side of the board, it doesn't trip the RCD on this side. So the only way we can do that is to install as a main switch an S-type or a time delayed type of RCD, okay? This is a 100 milliamp time delayed RCD. This is a 30 milliamp ordinary RCD. So if this RCD trips, this RCD isn't going to recognise the fault for at least 150 milliseconds, by which time this will have tripped with a bit of luck, okay? So what I'm going to do is I'm just going to show you how this works. I'm going to do an RCD test. You can only do it with an RCD test instrument because we're really measuring the time that it takes to switch off. If you've got a BS RCD, it's going to trip it, or should trip in 200 milliseconds. If it's BSEN, it must trip within 300 milliseconds. BSEN would be really a circuit breaker, an RCBO, okay? So if I now turn this to 30 milliamps, which is what the rating is of this RCD, turn it to times a half and plug it in. Okay, now, switch it on, tells me there's voltage there. If I now push the button, it shouldn't trip within 2 seconds. 2 seconds is the vital time, okay? I now set this to times 1, which is going to allow an imbalance of 30 milliamps within the RCD. At this point, it should trip within 200 milliseconds, okay? Because this is a VS type. Push the button. It's tripped within 200 milliseconds, it's 34.9. So perfectly okay, less than 200. But of course, that's only on one side of the waveform. If you see, that's got a 0 there. What I really need to do is test the current going both ways. So I push this button here, and now it's telling me it's 180 degrees. Turn the RCD back on again, push the button. Again, it's tripped within 26 milliseconds, which is really quick. As I say, 200 is the maximum. I now set this to times 5, turn it back on, push the button, 12.6 milliseconds. Need to do it at 180 degrees, turn it back on, push the button, and it's tripped within 6.8 milliseconds. So that's very fast, because on times 5 it should trip within 40 milliseconds. So this RCD is perfectly okay. Everything's working as it should be. On every 3-phase installation, it's important that we measure or check that we've got our phase sequence correct right through the whole of the installation. That would require it being carried out first of all at the origin of the supply, and then at every distribution board. For that, we need an instrument that will measure phase rotation, or a phase sequence tester, whichever way you call it, it means the same thing. The idea is that line 1, line 2 and line 3 run in that sequence, okay? This instrument here has got phase rotation on it. Very, very simple test. just connect our leads up onto the 3 phases or 3 lines, turn it on to phase rotation, and we should, with any luck, see it comes up and it says L1, L2 and L3, which shows quite clearly that the phase rotation is the right way around. If I connect it a different way around, we can see what the problems would be or how it would show you that it's the wrong way around. And just for demonstration's sake, I've swapped the 2 leads over. We've now got blue, red and green rather than red, blue and green. If I turn it on to phase rotation again, we'll see that it will come up the wrong way around. And we've now got L1, L3 and L2. So you can see that it's flashing, which is indicating that there's something wrong. It's a warning, and it also comes up visually so that you can see that it is connected around the wrong way. So that's phase rotation. Another way of measuring phase sequence or phase rotation is to use an approved voltage indicator, which has got the facility for phase rotation on it. This is a particularly good one, and all I need to do really is, these are indicated L1, L2, okay? So if I put L1 on line 1 and L2 on line 2, you can see that there's a green light against the R on the right-hand side of the indicator. Okay, that tells me that the rotation is correct. I now need to use L1 on L2, and L2 goes on to L3, and you can see, again, that's telling me that the phase rotation is correct. I then go the other way round, and I need to go L1 goes on L3, and L2 goes on L1, and again you can see it's showing me that the phase rotation is correct. And again, just by way of demonstration, if I get it round the wrong way, and I go L1 onto L1 and L2 onto L3, you can see the left-hand green light lights up, which is telling me the phase rotation is the wrong way. Nice simple method which we can use in any instant. We've got a 5-panel system here, and each panel has an open circuit voltage of 46.8 volts. So if we multiply 5 of those together, we end up with a value of 234 volts. It's important that I make sure the system is working correctly. The voltage isn't going to be spot on because we've got temperature values which make the voltage change slightly, and just the brightness of the sun. So what I need to do is turn this off. I'm going to use my clamp meter set to DC voltage. Switch it back on. And I've got a value of 230.1, which is really, that's as close as I'd expect it to be. And that's telling me that the system is working as well as it should be. In this country, the sort of weather conditions we get, the effect of temperature against voltage is very, very small, to be honest, so it's not really worth considering. Although for some exams you do need to carry out the calculation. To ensure our PV system is working correctly, we also need to check the short circuit current to make sure that it coincides with the amount of sunlight we get. Our panels are rated at a short circuit current of 5.76 amps. And what that means is that they'll generate 5.76 amps when the sunlight is producing an irradiance of 1,000 watts per square metre. Now, of course, our sunlight isn't always going to produce 1,000 watts per square metre. Sometimes it's going to be far less. So we need to carry out a calculation. And obviously, if our panels are rated at 5.76 amps and we're only getting 500 watts, they're only going to generate half of the current that they'd be expected to. So I need an irradiance meter. I need to measure the strength of the sunlight, so the irradiance of the sunlight. I've been outside and taken a measurement, and I've got a value of 833 watts per square metre. I now need to carry out a short circuit current on my system to make sure that my value of current is proportional to this. The calculation you need to convert the values we've got to the actual current that we're going to expect would be to multiply the short circuit current value of the panel, which is 5.76, by 833 and divide the sum by 1,000. But to make life easier for myself, I just convert the 833 into 0.833. And if I divide that into 5.76, I end up with 4.8 amps, which is approximately the value I'm expecting to get. Having calculated the value of current I'm expecting, I now need to short circuit the system and take a measurement. So first of all, I need to make sure the inverter is isolated. I then join the plug and the socket from the panels together, therefore creating a short circuit. I turn on the isolator, and then with a clamp meter, I need to take a measurement. And there we are, we can see that the measurement I'm getting is indeed 4.8. So that's just showing me that my system is working as well as I could expect it to be. The thing I need to remember now, of course, is because this is a DC system, when you pull the leads apart under load, you're going to end up with a big arc. So I really need to make sure I isolate this first. Once it's isolated, I can then disconnect it and reconnect the inverter. Once you've installed a photovoltaic system, it's important that you carry out a range of tests to make sure that everything is absolutely safe, because, you know, as you know, PV is DC, and DC inside a building can cause all sorts of problems unless it is put in very, very carefully. What we've got here is a rig that we've made up just for testing and to explain to people how the system works. We've got a main isolator up here, which is really for our use, and the instructors would use that to isolate the whole of the system. The PV isolator that we use for training is here, and we've got a little plate there with our connections that we can use to take different values of readings. The first test we're going to do is an insulation resistance test. So our panels are outside, everything's fully operational, but of course, and it's going to be operational because you can't isolate a PV panel once it's exposed to sunlight. The only way you can do it is disconnect it. And of course, if you're going back after a period of time to carry out a test, it's not particularly practical to get onto a roof and start trying to mess around disconnecting PV panels. So it's quite safe providing you follow the right procedures. What you would normally do is turn off the isolator and remove the cover and just use probes. But for us, we can do it by using this isolator here and these contacts. So the first thing I do is I turn off the isolator so the whole thing is completely dead. Then I use two leads which I've got and join them together. Now, of course, what you could do is you could use a probe and test your line and your negative conductor separately. This just saves me a little bit of time. Insulation resistance, so the instrument's set to insulation resistance. I connect one probe to a known earth and the other probe to the contacts that are joined together. When I turn this on, of course what I've done is created a short circuit at the PV panels, but that's going to do no harm because they can't generate more than they're made to generate. I now take a value of resistance, insulation resistance between this contact and the known earth, push the button, and you can see that I've got a reasonably high reading there. It's 200 megohms and creeping up, and it will continue to creep up until it reaches a very high level. So at this point, we know that that's quite a safe installation as far as insulation values goes. Important to remember before I touch anything at all, turn off the isolator, and then at that point I can disconnect all of my connections. Of course, we've made life easier for ourselves to carry out these tests by inserting these test points, but under site conditions, that wouldn't be available. So all you would do is you would turn off the main isolator, disconnect the two DC cables from the inverter, and you would have a male and a female plug and socket with bare ends. You join them into the disconnected leads, twist the ends together, connect your instrument, and then turn on the isolator and carry out your readings that way.